Hello everyone, I hope you can hear me. It would be nice if you can let me know if you can hear me or not. I was on the Senate meeting of the university and it wasn't ending, so I had to leave the meeting. But yeah, so here we are again with the live mathematics discussion. Please do post your questions there. We are going to be talking about engineering mathematics still. And what I'm going to do right now is to make sure that the Discord participants are also able to access the Blackboard. And then we get started. Okay, so hello once again. Hello also to the Discord participants of the stream. It would be nice if you can let me know if you can hear me, both on Discord and YouTube, just to make sure that... Great, so thank you very much, Mpela, for your reaction on YouTube. And would be nice if someone on Discord can confirm also that they can hear me as well. And then we're ready to start. I'm very sorry for the delay. There was another meeting, the University Senate meeting that I had to be at. And the meeting is still continuing, so I had to leave that meeting for the session. Okay, so nobody says anything on Discord, but I'm kind of assuming that they can hear me because the microphone seems to be on and also the screen seems to be on there. Great, so let's get started. I do not see any questions from anyone yet. If there are no questions, maybe there are some suggestions for a topic of what we could discuss. One important thing that perhaps we should mention is that now that this is the last week of classes, and soon you will be writing the A2 paper for the engineering mathematics course, it is important to mention there that what will be very useful for preparing for that paper is integration of knowledge. Different parts of the course gave you different pieces of mathematics, and then it will be important to understand how they fit together, especially to keep in mind how various concepts come into play in practical problems. This is something that you would have already received some kind of training in a way through the tutorial tests, and then also the video lectures that I prepared give that exposure because I was explicitly discussing the topics that connect various things. Okay, so at the moment still no requests for any specific topics to be discussed. So in that case, what I would like to then do is perhaps to come up with some questions to the audience, and then we can take the discussion from there. Okay. I think one of the subtle topics in the course is the topic of vector spaces, and specifically the concept of a subspace. So here is a question about subspaces that we could have a look at. Consider a differential equation given by second derivative of y plus 2 times y prime equals 0. And let's look at the question that asks the following. Is the set of all solutions of this differential equation, and let's give it a name, so let's call it equation 1, is the set of all solutions of 1 a subspace of the vector space of all functions? Okay. Would anyone like to give a try to answer this question? Of course, we will now have a discussion as to why this is or is not so. No feedback yet. I hope Discord participants can hear me. Would be nice if you can say that or not. And also those joining through YouTube, would you like to post an answer to the question? It takes a while for me to see that, so I'll wait a couple of seconds. Okay, so while you're preparing the answer, let me clarify a little point here. What is the set of solutions of 1? That's the first thing we want to clarify. And the second thing we want to clarify, what is the vector space of all functions? We need to know what these things are before we can say if one is related to the other through the subspace relationship, right? I just now I received a request from on WhatsApp whether this could be saved and then posted on Sunlearn, and the answer is yes, of course. We'll be doing this all the time. So the recording of this live session will be on Sunlearn, like the other 2 recordings we've made. Okay, so here's a very interesting question from Harry as a counter question to my question whether this includes the 0 as a solution. So that goes back to the question of what is the set of all solutions. When we say in mathematics all, we mean all, right? And when y is equal to 0, this function, if I substitute this function into the differential equation, we will get second derivative of 0 plus 2 times first derivative of 0 equals 0, which is definitely true. And so that makes y equals 0 as a member of that set of solutions of 1. So the answer to Harry's question there is yes, 0 is included into the set of solutions. The only weird thing about 0 is that we excluded it in the eigenspaces. So that's now a completely different world where the vector space is not the vector space of functions, but it's a vector space of column vectors, right? Or n-tuples of numbers or vectors in an n-dimensional real vector space. And so when we exclude the 0 vector to be an eigenvector there, that is a slightly different story to this one. But yes, 0 got excluded, but yet it got included in the eigenspace, right? So 0 vector is not an eigenvector, but still the eigenspace includes 0 as well. So it was only in that specific situation that 0 got excluded. Otherwise, in all other situations, we do want to have 0 in there. So let's look at the set of all solutions. First of all, how are we going to write it out, what it is? so how would we write down in mathematical symbols the set of all solutions of 1? Well, this is not something that in the class we've been trying to learn a lot, but it might be useful for me to point this out because we've used this notation a little bit for other situations. So this is how we can write it down. This is the set symbol, the curly bracket there, and then we say, okay, we're going to consider all things of this shape, and that means all functions, because usually we use y to represent a function. But if I want to be more explicit, I could say y is a function with that domain, with that range, whatever extra information I want to put here. But for the sake of this discussion, we're going to just put a y there, having in mind that y represents a function. And then on the right-hand side of the vertical line, we're going to put the equation down. And so then the way this thing reads out is that we've got the set of all functions y that satisfy the equation. Remember, this part in the set is the property by which things are selected. If you've been watching some of my earlier videos, you would know that by now. So we are selecting all possible functions having that property. And so that's exactly the solutions of number 1. So this is the set of all solutions of 1. And if I plug it in 0 in here, as we already talked, we would get the equality to hold, and therefore 0 is also in the set of all solutions. So that's what the set of solutions looks like. Now, the next question is, what is the vector space of all functions? And there we might, so okay, let me first link this up with that, and I'm gonna write this now in orange to link up with the other sentence there, the phrase there rather. So these are all the functions without any requirements on the functions, so except that the values of the function should be real numbers. So maybe we could even write it like this. I mean, something that we omitted in the previous expression, now it becomes essential we include it here, otherwise we end up with just this, which would represent only one object in the set, and we want to have more than one object, so that's why we have this vertical line to indicate that we are allowed to vary the left-hand side here as long as some requirement is met. And the requirement we have on y is that y is a function that's defined on let's say in this case, for the sake of this equation, let's consider the domain to be all of the real line, and then all functions that are defined on all the real numbers and whose values are some real numbers can be then represented as arrows from R to R. So there are many of them. So this part says that y is a function with a real function with domain the real line. Okay, so that's the second thing. That arrow, by the way, is not a vector. That's a symbolic way of writing down a function. Okay, so now we see here that anything that satisfies the differential equation will be such a function, just because of the assumption we made here that the y represents a function. And so then this set, the yellow set, becomes part of this bigger set. But of course, in the vector space, we don't only have just the set, we also have the structure of how we add vectors and how we multiply them by scalars, right? So let's indicate that if I have two functions, y1 and y2, how would I add them? Well, their sum will be a new function whose value at x is given by the sum of the values. So this is the rule for adding functions. And in practice, when we add functions, like for example, when we take something like y1 equals cos x, and maybe I should say y1 of x equals cos x, right? And y2x equals sine of x, then y1 plus y2 will be a function whose value at x is the sum of the values, so it will be cos x plus sine x. So that's the idea there, okay? With the addition of functions. And in a similar way, a function multiplied by a scalar is a new function whose value at x is equal to the k scalar times the value of the function. And so these three ingredients make up the structure of a vector space. Otherwise, just the first one alone, without the other two, will only be a set. It will not be a space. For us to have a space, we need to have a set with structure. Remember, set alone is just some chaotic, unorganized entity of some abstract objects, and so that it doesn't have any structure. And the structure is given by knowing how to add things and how to multiply things by scalars. Of course, this structure that we require for a vector space is much less than what the actual structure of the space in real life. Real life spaces have much more complex structure, and certainly we don't understand its full structure yet. But the whole point of mathematics is to abstract away to the point where we have something more manageable for our minds to grasp, and then work with that and see how much consequences we can derive from that. Okay? Great. So here we are now with the explanation of the question. I still don't have any answers, and so then I'm going to answer the question myself. So the original question was whether the set of all solutions of 1 is a subspace of the vector space of all functions or not. And the answer is, in fact, yes, it is a subspace. And the reasons for this are the following. So let me maybe give them some names. So let's call this thing D, because it's a set of functions given by a differential equation, and let's call this thing a V. Not just this thing though, the whole three things together. So the entire vector space of all functions. Let's call that V. That's just a temporary name, just for the purposes of this discussion. I can see that what I've shown there doesn't fit on the screen, so I've fixed that now. Okay. So we've got that V, that D, and the question is whether D is a subspace of V, and the answer is yes, and we will now explain why. So yes, D is a subspace of V, and let's see why this is so. Okay, so in order to understand why something is so in mathematics, what you need to do is to look into the definitions of the concepts involved. And in this case, the concept involved in the story is, of course, the concept of a subspace. So let's try to recall what it means for something to be a subspace or not. And then we will apply that definition we have for a subspace to this particular situation, and that will guide us how to verify or not whether this is a subspace or not, and then if it is, how to explain why this is so. Okay, so in general, the definition of a subspace is the following. So when we have a vector space V, something which is its subset is a subspace. So D is a subspace of V if and only if, and that I with double F represents mathematical both ways implication. So it means that what I'm going to state afterwards will be a synonymous to having D a subspace of V. So if and only if the following three conditions are met. Actually, I'll make it into 4 right now, just to make clear that D must be a subset of V. So in other words, every vector in D must lie in the space V. So if you take D to have something outside this space, then it can never be a subspace of V, just because of that. So and remember, these conditions need to hold all of them, so as soon as one of them breaks, then we're done. The thing is not a subspace. And in this case, the condition is satisfied because D was all solutions of the equations, and solutions of the equations are functions, and V was all functions, so every solution is a function, so everything in D is in V as well. Okay. Maybe I should just remark here, when I say every vector in D, I'm assuming here that D is a set of vectors, and so otherwise I should say every object in D, because really the condition says that everything, the whole contents of D must be made out of some things that are already in V. Okay, so that's the message for the for this first requirement. And then the second one is that the zero vector must be in D, and this is the zero vector of the space V. And the third one is that if two things are in there, okay, so this symbol here that I've used just means that 0 is inside D. So let me actually not use this symbol. So let me just say it like this rather. And then if V and W are in D, then it should follow, and that's the mathematical then symbol, that their sum is in D. And this should be true for all possible V's and W's, okay? Not just for one specific pair of V and W, but all possible VW's. And then we have that if V is in D, I keep using that symbol, if V is in D, then K times V must be in D as well, and then again, for all possible vectors in D, as well as for all possible scalars K. So K here can be an arbitrary scalar, and yet that condition should hold in that situation. Okay. Anytime if you have any questions, please let me know so that I can address them. So these are the conditions that would make D into a subspace of V, and that comes out just by the general definition of what it means for something to be a subspace. And now let's see how we could apply these requirements in this specific case. Now let's recall what D was. D was the set of all solutions of y double prime plus 2y prime equals 0, right? So let's recall that equation. So y double prime plus 2y prime equals 0. So for something to be in D, it means that it satisfies the equation. That's how the D was defined. So let's go through these conditions. Actually, we will not even write anything down now. We will use our existing knowledge maybe to skip writing anything down and come to the conclusion. So let's look at the first property here. Is every vector of D in V? Well, we already discussed that. Solutions of these are functions, and V has all functions in it, so it's true. So the first requirement is satisfied. What about the zero vector? Is that in D? Well, what's the zero vector in the vector space of functions? In the vector space of functions, and that's a separate topic, let me know if you want to discuss that or not. In the vector space of functions, the zero vector is the function who is constantly equal to 0. And if I take that function and substitute in the equation, I will see that the equation holds. Therefore, that function is indeed a member of D, because D has all possible solutions of this. And the solution, of course, is all possible y's, which when I substitute in the equation, make the equation hold. So then we find that the zero function is in D, but zero function is the zero vector of the vector space V, and therefore that condition holds as well. I see there is a question there now on YouTube. I'm going to read this question out and then either answer immediately or answer it after we discuss this, we finish this discussion. Okay, so the question is about matrices, and so we will move to that question immediately after we finish this discussion. So now if we pick two solutions of D, in other words of the differential equation, so if V and W are in D, so we pick two solutions, would their sum be in D as well? Well, we know this principle called the superposition principle, right? And according to the superposition principle, if you've got two solutions of the homogeneous equation, their sum is still a solution of the same equation. So then the answer is yes. And by the same superposition principle, if something is a solution of the homogeneous linear differential equation, then its scalar multiple will also be a solution. So the fourth one is yes as well. But just in case you're wondering how would you write this out without referring to the superposition principle, well, one thing you could do, I'm just going to illustrate this for the last one. You could say, okay, so let's pick a V in D. If V is in D, then V double prime plus 2V prime will be equal to 0. Then let's multiply V by K and let's see if it's still in D or not. So we have to substitute that in the equation and see if the equation still holds or not. Okay, and so when we derive this thing twice, because K is a scalar, we will get this. And of course K factors out here, and because sorry, I needed to put there 2V prime, because this thing is 0. Why? Because it was assumed that V was a solution, right? K times 0 will still be 0, right? So that shows, yeah, so the thing is that v double prime plus 2v prime is 0, therefore, so the actual chain of implications here goes like this. We've got this by the assumption, therefore, we have this, therefore, we have this, therefore, we have this, and therefore, we have that kv is in D. Because to be in D means to satisfy the equation. Okay? So that's how you could argue this out if you don't want to refer to the principle of superposition. But of course, what we've done here is nothing other than to prove the superposition principle in a very specific case, when we're just multiplying a solution by a scalar, and a similar approach could have been done also for the addition check here. In general, I should say that being a subspace can be equivalently described, these three conditions can be equivalently restated as D being closed under all possible linear combinations. So that's 0 gives the empty linear combination, and with plus and scalar multiplication we could have built arbitrarily long linear combinations, and so closure of these two separately is equivalent to closure under all possible linear combinations, and then that of course is exactly the superposition principle for homogeneous equations. Okay, I'm going to stop here. There is a lot more to say here, of course. The fact that, for instance, the span of D, the basis of D will be exactly the fundamental solutions of the differential equation, and because it's a second order equation, there will be two linearly independent fundamental solutions, and therefore D will be a two-dimensional vector space on all things like that. But these are discussed in some of the videos, and if you have a specific question about that, you're free to ask. Great, so I'm now going to stop with this question. We've explained that D is indeed the subspace of V. Why? Because it satisfies all the four requirements for a subspace. And now Devin asks to expand on how the first axiom holds. I hope Devin is referring to this one, that every vector is in D must lie in V. And so here is the expansion. So by definition, D was made up as the set of all functions y that satisfy this equation, whereas V is a set of all functions. So of course, every function that satisfies this equation will be a function in particular. So it's just like saying the set of red apples is part of the set of all apples, yeah? Or saying African human beings are part of all human beings. Or saying Stellenbosch University students are part of all students around the world, right? So functions satisfying this equation are part of all functions. That's what the first condition says, and that's why it holds. I hope I answered Devin's question. If you're not satisfied, Devin, please let me know. I'll try to expand more. Okay, so now at this point I'm going to move now to Salvatore's question. Can we expect to get a 4x4 matrix in the exam where we're required to find the eigenvalues and corresponding eigenvectors, because it can become quite tedious to solve the determinant? Okay, so the problem with me answering a question like this is that I have seen the exam. The good thing is I don't remember all of it. So if I say yes, most definitely, then I will be kind of giving out what I've seen. If I say no, then it's similar, right? If I say I'm not sure, then I will feel guilty that I knew the answer and I couldn't tell you more precisely. So I'm going to pretend that this question was asked to me before I saw the exam, and then in that context my answer would have been yes, it's possible that you will get a 4x4 matrix where you're required to find the eigenvalues and the corresponding eigenvectors. However, we will make sure, if we do put such a matrix in the exam, we will make sure that it is such that computations are not too tedious. So that's the answer to Salvatore's question. Okay, so any other questions? There doesn't seem to be any yet. So then what I'm going to do is the same as I did before. I'm going to randomly pick some topic and then discuss that. Perhaps I would want to, I think one of the soft points is this topic of subspaces. So maybe what I want to do then is to talk about subspaces in the context of the eigenvalue problem. Or I'm having some second thoughts now. Perhaps not, unless you request that. Perhaps instead what I want to discuss is the following. So with the whole story of eigenvalues and eigenvectors and the matrices and all of that, there were a few subtle theoretical points which I'm not sure to what extent the students would have necessarily taken care of noticing and looking deeper into them. And I want to maybe make some of those points more apparent. I will probably not cover all of them, but just to raise awareness, I will make some of those points more apparent here. For example, here's a question to you. Occasionally I can hear someone, but maybe they don't want to talk, but anyhow, if you want to say something, please do so. So let's look at the problem of diagonalization. So imagine I have a matrix A whose entries are 1, 2, 3, 4, 5, 6 there, and then there is X, Y, and Z. Okay, so there is a question from Deborah. I'm going to look into that after I complete this discussion. So imagine we've got a matrix like this, and there is some information given. So some entries of the matrix are given, but now the other entries are in the form of variables, so we don't know what they are. And imagine we are told that the matrix has the following eigenvectors. I must be careful here because it might very well be impossible for the matrix to have these eigenvectors. Okay, this is definitely not the case. I don't think this matrix can have these eigenvectors, but it would still make my question meaningful. If we are told that these three are the eigenvectors of the matrix, would we be able to tell what these entries of the matrix are, what the entries X, Y, and Z are? So could somebody answer that without any calculation, by the way? So here we do want to apply just those subtle theoretical points to answer the question without having to do any calculations. By the way, let me repeat that if you do calculations, you might discover that it's impossible for a matrix of this kind to have those three eigenvectors. I'm actually not quite sure about that, but that's beyond the point. Imagine that it's possible. If it is possible for a matrix to have these three eigenvectors, then what would be the entries of X, Y, and Z? Okay, so I give you a minute or two to answer that. Not a minute or two, maybe 10 or 20 seconds. Okay, so you can still answer while I'm talking. What we notice about these vectors is that they are all orthogonal to each other. If you take the dot product of any two of these vectors, you will get that the dot product is 0. And if we have a matrix with a 3 by 3 matrix with 3 orthogonal eigenvectors. Okay, great. Devin is right. and also Harry is right. So if we have a matrix with 3 orthogonal eigenvectors, that matrix would be orthogonally diagonalizable. And we know from theory that orthogonally diagonalizable matrices are exactly the symmetric matrices. So you see, just from that information from the theory, we can conclude without any calculation whatsoever what x, y, and z are, because for this to be a symmetric matrix, x needs to be 4, y needs to be 5, and z needs to be 6. And there are many other such situations where you could apply the knowledge of the general theoretical facts to make conclusions without having to go through tedious calculations. And that aspect will definitely be relevant for the coming paper. As you might have seen, it was relevant for the tutorial tests. So you see, with the, I mean, I don't want to step over on the toes of the convener here, but who is the one who is setting the papers, but I mean, it's kind of generally expected that with the online assessment, it would kind of make a little, not too much sense to have questions which are completely computational based, because you can have that calculated on the desktop, plug things in and calculate things without you having to do any calculations, right? And so you do expect that the questions will be a bit more theoretical than it would have been in a normal exam situation where you don't have calculator with you, or at least you're not allowed to use it explicitly, and that's monitored and so on. So please take note of the theoretical points in the module, and specifically how they can be useful in figuring certain things out on concrete questions. And so here is one example of that kind, and you can look at the tutorial test for other examples, and also you can try to kind of explore this topic on your own, where you look at the theorems that we did, and then see in what situation and what kind of application you could derive from those theorems. Just by thinking and reflecting about these things, you will come to some useful facts that will be beneficial for the completion of the A2 paper and A3 as well. Okay, great. So now let me go to the question of Deborah, who asks whether I can explain how to identify conic section when it's an ellipse. Deborah, I think you got me there. I need to recall myself how the equation of the ellipse looks like. So if I understand the question correctly, okay, so first of all, let's draw an ellipse. We all know how a circle looks like. A circle looks like this, right? And an ellipse is a stretched version of that, right? Now the equation of a circle, of course, looks like this: x squared plus y squared equals some r squared. What about the equation of an ellipse? How does the equation of an ellipse look like? And we're gonna make use of the fact that an ellipse is a stretched version of a circle. So you're stretching basically the variables x and y, and the stretch effect on a variable is to multiply the variable by some number. And then when you plug it in the place of x and y, you will get that number squared as well. So an ellipse equation should look something like this: x squared divided by, maybe I should put it this way, x multiplied by some k squared, or maybe rather divided by k, depending on whether k represents stretching factor or whether 1 over k is the one. I'm going to explain that in a moment. So if we have something like this instead of what we had originally, but of course this simplifies to x squared times some a plus b times y squared equals r squared, where both a and b are positive numbers. Actually, they have to be strictly bigger than 0. Okay, then we get the equation of an ellipse. And as I go along with answering this question, I would really like to request Deborah to let me know if I'm on the right track, if I understood the question the right way. So once you do that diagonalization thing and transformation of the equation into a form that doesn't have the xy term anymore, then you want to see if it matches this shape, and if it does, then it's an ellipse. Now, how did I get this thing? Well, imagine I'm trying to figure out what are the coordinates of some point on the ellipse, right? Okay. This coordinate, in this specific case, the stretching factor for the y coordinate is 1. You see y didn't get stretched, only x got stretched. So what I want to do, I want to go back here. Go back here. But how do I go back? So this is the stretched version of that one, right? So if the stretching was by factor k, then to go from here to there, I have to divide by k. So that's why I'm dividing by k here, because now I want this x divided by k to fit together with the y in a circle. And so that's the same as taking the circle and stretching it. So in the coordinate, I want to reverse the stretching procedure so that I then plug it into the original equation of the circle. So that's why we have divide by k, where k is the stretching factor, not by not multiplying by k. Okay, so Deborah gave me a reference for the question in chapter 8.12, question 31, and I'm going to look at that question in a moment. But yeah, so the summary is that we do the standard method of transforming the coordinate system and getting the orthogonal diagonalization and everything of that 2x2 matrix. And then once we simplify the equation needs to look like this in order for us to say, aha, it's an ellipse. As for the question by Arno, what conic sections formulae are we expected to know for the exam? All of them. So you need to know, well, again, I mean, I'm answering this question pretending that I didn't see the exam yet. I actually don't remember whether or not there are conic sections in the paper, but it doesn't mean there aren't, and also it doesn't mean that there is, so I don't have any information on that. So the various conic sections are the parabola and the hyperbola, right? The two lines. I think this is something that you would have done in the first year, the circle, the ellipse, and so on. So this is something you would have done in the first year, and please have a look at that. There is also a section in the textbook where this classification is made according to the shape of the equation. How can you see what curve it is? I'm hearing some echoing. I wonder if somebody is joining by voice. Anda, do you... I think there's somebody called Anda. Anda, I can hear you a little bit. Do you want to either mute your microphone or talk in a separate space or something like that? I'm gonna get the textbook now to look into Deborah's question in more detail. And then after that, I'm going to look into Devin's question. Okay, so I'm back. The question that I was referred to for conic sections was the following. So we have 5 x squared minus 2xy plus 5y squared equals 24. And what makes it difficult to see what conic section this is of course the minus 2x part. So the matrix method we're going to use here is the one that allows us to eliminate this, but then the shape of the equation changes, obviously. Let me just remind you how that works. I'm not going to go through all the detail. If you do want me to solve this question as in a separate video, I will be most happy to do that. You just make a request to that, and I'm going to then make that video. So we set up a matrix for this, and remember the coefficients of these go in the diagonal of the matrix. So we have 5, 5, and then half of the xy term goes in here. And then we have this, and we equate that to 24. And what we want to do after this is, so we're lucky here we don't have the x, y term separately. That will make calculations easier. Okay, thank you Arno for the hint. I think I should mute somebody called Anda. Okay, so by diagonalizing this matrix, we will get what we want. And okay, so let's diagonalize this matrix. What will be the... To do that, first we'll have to find eigenvalues. And so the eigenvalues of this matrix will be what? Let's have a look. I actually end up solving this question, I think. Okay, so we want to get the determinant of 5 minus lambda minus 1 minus 1 and 5 minus lambda here, right? And that equated to 0 to get the characteristic equation. And so that will be 5 minus lambda squared minus 1 times minus 1, which is 1, equals 0. And we can solve this by saying, okay, 5 minus lambda squared must be equal to 1. So 5 minus lambda must be equal to plus and minus 1. You see how I'm using a non-standard way of solving the quadratic equation, right? And then, therefore, lambda is equal to 4 and 3, right? So both 4 and... No, wait a second, sorry, what I'm talking about. So it's not 4 and 3, it's 6 and 4. So these are the possible values. Yeah, 6 and 4. 5 minus 6 is minus 1, and 5 minus 4 is 1. So these are the possible lambda values. And when you put this in the equation, right, you will get... So the diagonal... Remember what happens with this? The new equation will now have the form... given by actually, so these x and y here are the old coordinates, and the new coordinates will be denoted by capital X and Y, can be denoted by capital X and Y, and they will give rise to another equation which will help us identify the conic section. And so the matrix here, instead of that, will be the diagonal matrix for this, which is then given by the eigenvalues in the diagonal entries. And so when you expand this out, you will get 6x squared plus 4y squared equals 24. And so you see we do have a situation where we have positive numbers in front of x and y. And so it does match with this shape, with a and b being positive. And therefore we can see that it's an ellipse. So let me know, Deborah, if I've answered your question. And if I haven't, then I would be quite happy to solve this problem in full detail on a video. However, keep in mind there is already a video on a question like this. I think it's for 34, where all the methodology is discussed. It's just that the shape of the equation is different. And so the main difference lies in this fact, the fact that we're getting now an equation of this form, and I've explained here why an equation of that form must be an ellipse, and so that should be then answering your question. Okay, So while I hear feedback from Deborah, I'm going to move to the next question, which is Devin's question. If I could please discuss what would happen to values and vectors of a matrix when the matrix is transposed and when we take the inverse of the matrix. Okay, so that's a good topic to discuss. I don't think I will have answers to all of these questions. Specifically, I don't know what happens in general for the transpose matrix, but in a particular situation I will be able to answer that. So let me first look at the inverse matrix, where I do know what to... okay, great, thank you very much, Deborah. So in the case of the inverse matrix, what happens to eigenvalues and eigenvectors? And I'm quite I quite like this question because wow, this is fantastic. Okay, if you want to have a moment of fun and joke, somebody says, "Can I pay you if you do my math work $30?" Crispy Brock, you will have to pay me $500 million if you want me to do math work for you for 1 second. So that's the rate I'm charging. Of course, this is just a joke, and it is a nice joke. So thank you, Crispy, for your humor. If you do need some math help, I can help you for free, because that's what I do. I provide free help for math. Being a mathematician, that's what mathematicians do. They develop new mathematics and give out mathematics for free. Okay, great. In general, I'm very much against any financial gain out of sharing of knowledge. I think it is one of the big things that humanity has to understand, that financial finances and knowledge don't go well together. Anyhow, I don't want to make any political conclusions from this statement. It's in the spirit of semi-serious conversation. So let me come back to the question. Let's take a matrix A, and let's take the inverse of the matrix, and let's see what happens for the eigenvector. So imagine A is some n by n matrix, and imagine we have some eigenvector for that matrix. So k is an eigenvector, ak will then be equal to lambda k. Arno, it will be a bit difficult for me now to look up that video, but I'll try to answer your question. If you're not satisfied, let me know, then I'm going to see what exactly was going on in that video. So ak equals lambda k means that k is an eigenvector for the matrix A, and lambda is the corresponding eigenvalue. And what we want to do now is to determine what's going to happen for the inverse matrix. So what about A minus 1? Okay, so what about it, right? Let's multiply both sides of this equality with A minus 1. Then we have A minus 1 A k equals A minus 1 lambda k. Okay, that's a good first step. In the second step, sorry about that, that was my mistake. In the second step, let us simplify the expression we got here. A times A minus 1 will be, of course, identity matrix, and that's, so that will just give k. And on this side, I could factor lambda out. I could take the lambda out because it's just a scalar. And what I could do now is to multiply both sides by the inverse of lambda. Then I get this thing equal to A minus 1k. And now I could rewrite this in a different way, where I swap around the sides. So we get A minus 1k is equal to lambda minus 1k. And so the conclusion is that if a matrix has a certain eigenvector and a certain eigenvalue, the inverse matrix will have the same eigenvector with the eigenvalue being with the eigenvalue being the reciprocal of the initial eigenvalue. Okay, so that's the answer for the inverses of matrices, right? We have to be a bit careful here though, because when we multiply it by the inverse of the matrix, first of all we need to know that the inverse of the matrix exists. So not every matrix is an inverse. So what I said here only applies to those matrices that have the inverse. So that's one remark. Now the other remark is that when we multiply it by lambda minus 1, we need to know that lambda minus 1 exists, right? But the only time when lambda minus 1 does not exist is when lambda is 0. And if lambda was 0 here, well, here, if lambda is 0, then we'll get k equals 0, and so k cannot be equal to 0, because k is an eigenvector. So lambda cannot be equal to 0 either. And in fact, for an invertible matrix cannot have 0 as... an invertible matrix is cannot have 0 as an eigenvalue, because if it does, it will force the determinant of matrix to be equal to 0, and so we will never run into the situation where we have a matrix that is invertible with a 0 eigenvalue. And therefore we can then say that any matrix having a certain eigenvalue lambda will have its inverse matrix having the same, not the same, but the reciprocal of that eigenvalue, and the eigenvector will stay the same. Now, what about the transpose of the matrix? Well, there okay, let me think about that question. At the moment, I want to say I don't know what happens there, but I know definitely in one special case, but maybe I can also give a general answer. So we have ak equal to lambda k again, and if we transpose both sides, then we're going to get transpose of k times transpose of a equals lambda times transpose of k. But now the a here is on the wrong side, right? We want it to have on the left side, and in general, multiplication of matrices is not commutative, so a times b is not equal to b times a. So I don't see that this gives anything useful, except of course in those cases when the transpose of the matrix is equal to its inverse. And then that's the case for orthogonal matrices. But of course when the transpose is equal to the inverse, then the answer is already given here, because transpose is the same as inverse, so we just restate the answer we gave here for the inverse. So I'm not sure if oh, thank you very much, Arno, for the reference to the example video to Deborah. So I'm not sure if I answered Arno's question. I hope I did. If I didn't, please let me know, Arno, and I can expand a bit more on that. So the short answer, the summary is that when a matrix has an inverse, its inverse will have reciprocal of the eigenvalue and the same eigenvectors. By the way, there is also a geometric way of understanding this, because eigenvector is the factor by which a vector gets scaled by a transformation, and if on the other hand, the inverse matrix is the inverse transformation. So if something got scaled by 5, the reverse process should scale it down by 5, right? So that's how the scaling factor becomes 1 over 5 when we go backwards. So that's the geometric intuition for why does the eigenvalue become reciprocal when we move from a matrix to its inverse matrix. And the algebraic explanation of the same thing is given here. Okay, great. I think I've answered the question. By the way, I should remark that the description you see here for Live Mathematics 3, that will be corrected. This is, I mistakenly copied the description we had for Live Mathematics 2. So the topics covered that's mentioned there, that's not the topics going to be covered now, that was the topics that were covered already previously. And so for this video, once we finish the video, then I'm going to look what topics we covered there, and the description will be updated accordingly. Okay, at this point I don't have any further requests yet about specific questions. So if there are any, please let me know, and then I'm going to respond to them. I just want to take maybe 1 or 2 minute break. We've passed 1 hour now, and so we'll resume in 1 or 2 minutes. Okay, I'm back. No questions came through. I would like to thank a lot Pepe for letting me know that apparently the delay between the stream delay for the YouTube stream is approximately 30 seconds. So when you ask a question, it will be like 30 seconds before I can read it. Okay, I'm sorry about this, Crispy. We are doing here some university mathematics. I'm also not quite sure exactly what your question is. If you want to expand on your question, we might be able to answer you. Otherwise, I think you're in the wrong spot here. But yeah, I'm still happy to see your question if you expand on it a little bit. Okay, so and good luck with the test, by the way. So let's continue with the discussion. Okay, so what comes next? Let me think. How about Laplace Transforms? This is something that we did a long time ago, and we haven't looked into it recently. What are the key points in the theory of Laplace transforms? Well, of course, the whole theory is geared to solve a system, not a system, sorry, to solve a differential equation. And on the other hand, the differential equations we solve, which are actually initial value problems, they come already from the previous work. Perhaps it will be useful for you to know that with the Laplace transforms, especially because the process of solving the entire differential equation is a long one, you might get questions which ask you about some middle step somehow of applying Laplace transform to solve a differential equation. And so what do we mean by a middle step? So let me give you some concrete example of that. I'm paging through the book as well so that my brain remembers what's going on there. It's interesting how memory works in human mind. The point of reference is sometimes useful. Maybe someone can answer Crispy's question for finding a missing side of a triangle. Oh, I see a question now from Arno. Suppose scalar multiplication on V is defined as follows. Okay, let's suppose that, Arno. What do you want to do with that? It is actually the usual way of defining scalar multiplication, right? Okay, I'm responding to Harry to show what the first question was before we started discussing it. Okay, so Arno is asking a very interesting question. Given that the scalar multiplication is defined coordinate-wise, would it be true that 1 times x will be equal to x? The answer is yes, and I also am not sure if you think it was marked in an incorrect way. So let me actually write something down to that effect. So if we have a vector space in which we define k times xy to be kx ky, then of course with this definition one times x y will be equal to 1 times x 1 times y. And so of course 1 times x 1 times y is xy, and so there we get what we want to get, that 1 times anything will be that thing. So I'm also not sure, Arno, why you didn't get a mark there. Maybe you want to send it to me through by WhatsApp, so we'll have a look at it. Okay, so I'm going to look into that, Arno, and then answer you afterwards, since it's a test-related question. I also can't find exactly where on Discord you send it. Crispy, I think there was a misunderstanding. What confused me was your message about the payment. So that's why I thought that maybe it's coming from a spam or something like that. If you're genuinely looking for help in mathematics, of course we would be happy to help you. I'm going to discuss this Laplace thing I promised, and then I'm going to look into Crispy's question. So for Laplace transforms, and especially for applying them in solving differential equations, let us point out what the main steps are. Okay, so consider a differential equation of the form, so I'll just pick one example there. Suppose the differential equation is something like this: y double prime minus 4y prime plus 6 times e to the power 3t minus 3 times e to the power minus t. And the very first point to keep in mind with solving differential equations with Laplace transforms is that we also need to have initial value conditions, because they will be used in expanding the formulas of the Laplace transform, right? So one difference between usual method of solving an equation and the Laplace transform method is that in the Laplace transform case, we're treating the initial value problem at once. Okay. Next, what we do is that we want to transform both sides of the equation, right? So for the left-hand side, well, first of all, let me write this down. Because Laplace transform is a linear operator, it will end up being Laplace transform of second derivative minus 4 times Laplace transform of the first derivative. And then here we'll have 6 times Laplace transform of e to the power 3t minus 3 times Laplace transform of e to the power minus t. Yes, Devin, I will be doing a live stream. I'm not sure when is the A2 paper. If it's before Friday, we can arrange something like that. Otherwise, the usual Friday streams are in place. So that's the first step, right? Then for these things, for transforming the derivatives, we're going to be making use of the transform of the derivative formula. As well as together with those formulas, okay? On the other hand, for the right-hand side, we will be we'll be using the standard formulas for Laplace. I'm sorry, sometimes when I get quiet, it's because I'm reading the messages on the YouTube. So on the right-hand side, we will get the Laplace transform formulas that we have for things like, I mean, specifically in this case, the exponential function formula that we'll be applying is that the Laplace transform of a general fact that the Laplace transform of e to the power a t is equal to 1 over s minus a. So you see, we're going to be dealing with the left and the right hand side in a different way. And so there might be a question asking you, okay, what are you going to do with the left hand side? What technique are you going to use? Or what technique are you going to use on the right hand side? So you need to have kind of understanding of what techniques we're using, and not just remember those techniques, but also be able to recognize them and give them a name, or maybe recognize a name if the name is listed as one of the multiple choices. Now, linearity is used in both cases, right? Now, once we apply the right-hand side thing and the left-hand side thing, then we get Laplace transform of y equals to some expression. And this expression will be typically given by a long fraction. And what we want then, after that, is to use partial fraction decomposition to decompose this into a linear combination of more simpler fractions. And then for each simpler fraction, we take the inverse transform, because the inverse transform is linear just like the transform is, and again make use of those formulas from the formula table. So you see, there is a story to which how the method works for solving a differential equation using Laplace transforms, and understanding this story is very important. So it's not sufficient if you just have procedural knowledge where you're given the equation, you can just lay it out and get this answer. You should also be able to kind of almost like know what to do without doing the calculations and saying, okay, that step we're going to be making use of that technique to arrive from that step to that other step. So from that point of view, those tutorial questions where it was asked to apply some procedure to do something, the calculations, if you've got that procedural knowledge, then also make sure that you can tell the story of what's going on and how each step relates to the theory topics. Like for example here, the topic of linearity of Laplace transform is coming in, the topic of partial fraction decomposition is coming in, the topic of transform of the derivatives is coming in. I don't know if this was very useful, but I kind of wanted to point out the importance of the structure of the procedures that we're doing and how the structure relates to the theory topics. Okay, the paper is going to be on Friday, so we can definitely have a stream before that. Then Harry is saying that he's not sure if there is a misunderstanding, but on page 356 and 357 it is said that the solution set of a certain differential equation is not a vector space, since y equals 0 is not a solution. That's very interesting, Harry. I'm going to immediately look into that question right now on page 356 and 357 of the textbook we're using. That's for engineering mathematics, but I think I have the wrong edition. At least my edition doesn't match with yours. If you can take a snapshot of that question and send me by WhatsApp, I'll be able to help you out there. It's possible that the equation was giving y double prime plus 25y equals some non-zero number, let's say 3. Then y equals 0 wouldn't be a solution, right? Otherwise, y equals 0, if this is 0 here, is indeed a solution. Okay, so let me now go to the question of Crispy, which is actually quite interesting question because of all the zeros appearing there. Usually in mathematics, when you've got some exceptional situations like situations which are not typical, which are usually given by the value of 0, some interesting things come out from there. So the question of Crispy is the following, that you need to find missing side of a right triangle. So we've got a right triangle there. I wonder if 0 represents actual 0 or if it's supposed to be a theta. So if it's supposed to be 0, then it's one of the angles of the triangle is 0. And of course, then the triangle becomes flat, right? One wouldn't even call it a right triangle. Imagine if this angle was 0 or that angle was 0. So I'm assuming that the angle is called theta, not 0. So 0 in this notation of the chat represents theta. And of course, then we use those formulas that sine of theta. So if I label these ABC, sine of theta is A over C, cosine of theta is B over C, over C, and tangent of theta is A over B. Now, when I studied this at school, in Canada actually, my math teacher told me that there is a nice way of remembering this. I mean, he told to everyone in the class. He had this name of certain person called So Ka Toa, and he claimed it to be a Canadian Indian, this person. What it stands for is that sine, as for sine is opposite over hypotenuse. So that's how sine of theta is A over C. Cosine is, so C for cosine, adjacent over hypotenuse. That's how we get B over C. and tangent t is opposite over adjacent, so that's how we get a and b, a over b. So using these formulas, it should be possible to determine the sides of the triangle once certain values of sine, cosine, and theta, tan are given and other sides are given. I hope that answers this question of Crispy, if he's still around, or he or she. Okay, great. So again, I don't have any further requests. I'm waiting for some of them. Okay. Okay, you're welcome, Crispy. Alright, so what else would be meaningful to talk about in the remaining time that we have? Well, let's ask the following question. What is the most difficult topic in the entire module? Please let me know your answer in the chat, either at Discord or on YouTube. Okay, Triven says that the most difficult topic is vector spaces. Let me unpack this topic a little bit. So, what is most important here is to get a feel of what a vector space is. Once you have the feel of what a vector space is, then things should become more manageable. Deborah says that the topic with matrices is the most difficult one. I actually agree with Deborah. Once at school, I miserably failed a test that had to do with matrices. Well, thank you, Crispy. Because I always used to make mistakes with calculations. Anyhow, the topic of vector spaces splits into several topics. The topic of subspace, the topic of linear independence, the topic of basis, so that we should still list it here, the topic of basis, but that topic is actually a subtopic of linear independence because basis is a special type of linearly independent sequence. And the topic of span, which is a subtopic of subspace, and basis is a common subtopic to linear independence and span. I think this picture gives a good summary of the entire topic of vector spaces. And so by making such diagrams of concepts, you can get some kind of guidance through how to kind of put all the things together. The thing is that each of these topics, subspace, span, basis, and linear independence, each of them are highly relevant in two separate places, in matrix theory and also the differential equation theory as far as linear equations are concerned. So, and those links have been mentioned, have been explained to me by me in the videos. But all of it would be, in fact, quite difficult to grasp until you have a fair amount of feeling of what this thing is about. And so an excellent strategy for learning things is to turn knowledge, factual knowledge, which might have required to remember things, into an actual experience of the subject. So it becomes part of your feelings. And if it becomes part of your feelings, then you automatically have what it takes. And so, but this transformation of knowledge into feeling is the thing that you want to aim at when you're studying. So when you're studying, the idea is not just to remember a whole bunch of things. When you're studying, the strategy should be to turn your knowledge, to make your knowledge so basic that it turns into a feeling and into something intuitive, something intuitive to you, kind of making the knowledge of your own. And once that's done, then you're a master of the thing. Okay, so meanwhile I got a snapshot of the page from the textbook. The general, it reads out as follows: the general solution of the homogeneous linear second order differential equation y double prime plus 25y equals 0 is that and that. A basis for the solution space consists of linearly independent vectors. The solution space is two-dimensional. I don't see anywhere that it says that this thing isn't a subspace. So you see, it even talks about the basis of the solution space. So now we have a little mystery here, what was being referred to. Okay. The next request is by Trivan, who says, please go through it again, sir, you lost me. Trivan, I would be happy to do that. Just tell me what I have to go through again, since your message arrived a bit after I said what I said. I'm not sure what I should go through again. So while Trevor says that, I'm going to answer Michael Knight's question. Okay, I will go through that vector space diagram again. But meanwhile, answering Michael's question, what is the difference between the Fourier and Laplace transform? Well, they are both integral transforms. Fourier transform makes use of complex functions, and Laplace transform doesn't. Fourier transform is used for solving differential equations, but as far as I know, for solving partial differential equations, as far as I remember now, whereas we use Laplace transform for a different kind of differential equation. In general, for various different kinds of differential equations, you have different methods for solving things. Fourier himself was working on the heat equation, which is a partial differential equation. Some of you will be doing that, by the way, in the second semester. And so that's how he came up with the Fourier series, and I think Fourier transform also is derived from that. Yeah, so I mean, I cannot tell you much more in the sense that I'm not going to go into detail now what is Fourier transform, but ideologically they're kind of similar things, similar tools, but used in slightly different circumstances. So that's my answer to the question what the difference is between the Fourier and the Laplace transform. I don't want to go into detail because we haven't done Fourier transforms, and I would myself have to look it up exactly the precise definition. But it's something similar to Laplace transform where we are using integration to transform the function. Okay. Trevor asks me to go again to the vector space diagram. Okay, so this diagram represents concepts, the key concepts that on which most of the work we did build on. Okay, so these are the key concepts, these 5 concepts, and in order to define one thing, you might need to know definition of another thing. So, in particular, it all starts with a vector space. So, this is the most primitive concept. You can't define any of the others below it if you don't know what a vector space is, okay? Once you know what a vector space is, then you can define what is linear independence and what is a subspace. As objects, they're quite different things. Subspace is a set of vectors having some properties. Linear independence concerns sequence of vectors. In the textbook, they also talk about linear independence of a set of vectors. But the point is that in the case of linear independence, we have order to the set, the terms that are ordered, like we could have vectors v1, v2, v3, whereas in a subspace, there is no order to the vectors, okay? So for example, on a plane, there's no reasonable way of ordering points on the plane. So linear independence deals with sequences, subspace deals with sets. They're quite different things. Then span is a concept. It's a procedure actually that allows you to build a subspace out of some set. And basis is a special type of linearly independent sequence that spans the whole space on one hand. On the other hand, it's linearly independent. So the ways these concepts relate to each other are completely different and specific. So one has to specifically understand each of these concepts, but then also to understand how they link up with each other. And furthermore, how they link up with the topics in the module, and specifically with the topic of the matrices, the matrix theory, and the topic of linear differential equations. I'm not sure if I did justice to Treven's request to go back to this diagram. Okay, great. So thank you, Treven. Yeah, so that's one thing maybe that we don't often talk about, and maybe that's a bad thing that we don't talk about, the importance of concepts and what are they. So let's spend just a couple of minutes discussing the idea of a concept. So there are lots of concepts that we acquire through our childhood without even realizing that we acquire them. One of the examples is the concept of a number. Numbers 1, 2, 3, and so on. Then the concept of a fraction, right? 1 over 2 is the same number as 2 over 4, but they have different representation. So you see, there is something going on, some mathematics going on in there, but it seems like very trivial to us because this concept is something we've already acquired. I mean, specifically here, the mathematics that's going on is that they look different, but they're yet the same number. Whereas in this world, if they look different, they will be different numbers, right? 11 looks different from 12, and no wonder because they're a different number. On the other hand, 1 over 2 looks different from 2 over 4, but they are still the same number. So it's not quite trivial what these things are, but nevertheless, we understand what they are because we've got the concept of the number. So a concept is, in a way, it's some kind of construct in our brain, right? With all the links that it has with all sorts of other concepts. And this construct in the brain it's not maybe only in the brain, maybe also in the mind, in our spirit, or whatever is there. Maybe everything is inside brain, maybe not, who knows. This construct in the mind or in the brain is integrated with our knowledge. So any area of life where numbers are relevant, we will be able to recognize them in that area of life because we've got the understanding of the concept. I mean, maybe you never counted coffee beans, right? But because you've counted other things like sticks or pieces of paper, you have the ability to count the coffee beans as well. Why? Well, you never taught specifically to count coffee beans, so how come you can count coffee beans without ever having done that before? Well, because you've got the concept of counting. So concept is an abstract thing, which a kind of ability you have, which whenever you need to apply it in a new situation, you can do it without any trouble, because the new situation is a special case of the abstract understanding of the concept that you've developed through specific examples, perhaps. So that's what you want to happen with every new concept that you learn. You want that concept to become part of who you are in some sense, so that when you're dealing with a practical application, a concrete situation, you can recognize the concept and make use of it in that situation, just like counting the coffee beans, even if you have never done it before, without any trouble. Now the question is, how does one build up such a knowledge of a concept that it becomes so powerful you can apply it in completely new situations to you? And the answer to that is quite simple. The answer to that is the following. So whatever new concept you are learning of, and so I'm going to now make a huge trivialization. I'm going to talk about the concept of an apple in the place of the concept of a vector space, but whatever I'm going to say about the apple will apply to vector spaces as well in terms of acquiring the concept. So imagine up to this point in your university or school studies, you've never before encountered the concept of an apple, and now in engineering foodematics, I'm teaching you about the concept of an apple. So I will teach you about the concept of an apple in the following way. First of all, I'm going to tell you, well, apple has this shape. Now, if you have never seen apple before, I just show you this shape, you will tell me this is too abstract. You will tell me you have no idea what this is, because it will be difficult to distinguish this shape from this shape, which is no longer an apple, but it's a leaf, okay? Or it could be some other vegetable or fruit, right? So just to tell you that apple has this shape is not enough for you to acquire the concept of the apple. I also need to show you specific apples, concrete examples of apples. I need you to take those apples and taste them, to get the taste of the apple. So that's you working on specific exercises on vector spaces. That's the analogy of tasting the apple. And in this process where we do various very concrete things with the apple, together with me telling you about the general properties of the apple, eventually the conception of the apple is being formed in your mind. And it becomes, at some point it obtains the level where every time you see apple, you will recognize it, and you will know that thing is an apple, and you will be able to distinguish apples from other things, and you will know how to apply them, and you will know how they taste. And so if they give you enough food, you will know in advance, without tasting the food, whether apple will suit that food or not, okay? And so the same applies to any concepts that we do. You want to go through this process of tasting it, reading up how it looks like in terms of the shape, looking at several different specific examples of the concept. And so this process, once you go through that process, then you eventually acquire the concept. So linking up concepts with other concepts is also very important, because if I'm going to tell you that apple is a special type of a fruit, you do want to start making comparisons between apple, pear, and watermelon, and what the differences are, and such comparisons will allow you to gain a better insight to the concept. In a similar way, we want to link up several different concepts once we look at them separately. So this is just a few ideas around how important the acquisition of concepts are, and how much work we actually have to do before the concepts become part of who we are. Okay, now coming back to some more explicit mathematics, Arno is asking, I would just like to clarify something. An n-by-n matrix A is orthogonal if its columns form an orthonormal set. That is right. The definition, so here we have an example of a concept, right? The concept of an orthogonal matrix. Let's talk a little bit about this. So if we have an n-by-n matrix A, what does it mean that it's an orthogonal matrix? Well, it means that its column vectors are orthonormal set. So A orthogonal means columns are orthonormal. And you notice how the concept of orthogonality now becomes relying on the concept of orthonormality. Okay, what does orthonormal mean? It means that if I now introduce numbering for these columns, let's say the columns are A1 all the way up to AN. orthonormality means that the norm of each vector is 1, and that's the same as to say that the dot product is 1 with itself. So dot product of AI and AI is 1 for all the i's, and dot product on the other hand of AI and AJ, or inner product, is the same thing, is 0 once I is different from J. Now this is me telling you how it looks like, right? I'm giving you the definition, but if you want to really understand this concept, you have to work out the examples. You have to take specific matrices and check whether they form orthogonal matrix or not by checking these criteria. And so that's the tasting of the apple part, where you get a feel of and also not just the tasting, but also looking at concrete examples of those things. With this process, then you eventually develop the feeling for the concept. For some of us, concepts in one area of life come easier than for others. For example, I might have a very good sense of concepts in music, whereas another person might struggle with it, or the other way around. Actually, since childhood, I struggled with music a lot, and so that was one of my passions to break through that struggle. So, so musical concepts came hard to me, but the mathematical concepts always came very easy to me, and maybe that's why I'm a mathematician. But once you break through the challenge several times, then something eventually does become easy. But yeah, so one has to work hard in those cases where one doesn't have natural ability to grasp the concepts easily. But the good news is that the working hard will reward, and eventually you do develop the intuition for grasping these concepts in that subject as easily as if you had talent for it from the early childhood. Okay, great. Any other things that you want us to discuss? Arno is asking, would you mind if I ask a few fact-checking questions, provided no one else has any specific... I don't mind that at all, Arno. So let's now engage in Who Wants to Be a Millionaire game, where Arno is going to ask for some facts, and I'm going to say yes or no, depending on whether they are true or false. Okay, so I'm ready, Arno, for your fact-checking questions. First fact. Eigenvectors from different eigenvalues are always orthonormal. So let me write this out. I want to say a few words about it. Eigenvectors from different eigenvalues are always orthonormal. Okay. Always not orthonormal, but always orthogonal. Okay, so this is false. This is not true. Here is an example that shows that this is false. I could have a transformation of the R-squared space, in other words, a 2x2 matrix, where I stretch this vector by factor 2 and stretch that vector by factor 5, okay? Sorry, by factor 3. Just by saying what happens to these two, the whole linear map can now be uncovered, because any vector on R squared will be a combination of these two linearly independent vectors. And so then these two will be eigenvectors with the different eigenvalues, but the angle between them isn't 90 degrees. And so then we have a counterexample to the claim that eigenvalue vectors for different eigenvalues are always orthogonal. So the answer is no. However, However, there is a case of certain type of matrices when the answer is always yes. So no in general, but yes for symmetric matrices. So that's the answer to that question, Arno. In fact, we have a theorem that says that a matrix is orthogonally diagonalizable, which is exactly ability to find orthogonal eigenvectors as long as there are n many of them, if and only if the matrix is symmetric. So this is very much a characterizing feature of symmetric matrices. Okay, so any other fact questions? Maybe I should tell you, while I'm waiting for any other questions, let me tell you a little story, a very short story. About a certain student in the engineering course, the same one that you're doing now. Many years ago, she was an average student. Her marks were between 50 and 60. And then at every tutorial, I would see that she would be, instead of solving the tutorial problems, she was looking at the theory part of the section and studying the theorems and their proofs and drawing some collages where she was relating concepts with each other and so on. And knowing what her mark was, I once even told her, look, you don't need to do that. This is advanced stuff. Why don't you just focus on the tutorial? We will not really examine you on those things that you're studying. And her answer was, well, but I want to know, I want to have the full picture. I want to understand all the details of what's going on. I was quite impressed with that answer. And it was no wonder, because by the end of the year, she was the top student in class. She got best marks, almost full mark, well, definitely a full mark for a test, and almost full marks for overall. Something interesting happened. In fact, the first test that she wrote in the second semester, she failed it, so she had to rewrite it, and she was like crying, and this is a disaster. And we just had like 5 or 10 minute chat where I explained to her that it's fine, everything is fine, that she just needs to maybe unpack things at a deeper level, but otherwise it's fine. And well, it was a bit more. She actually prepared for a certain video presentation for a seminar that we were doing together with other students as well, and somehow her mindset about mathematics changed. And in this, on the rewrite, she got full marks, and then eventually she became top student in class. So it's remarkable to see how much jump one can make just by switching from this way of thinking of computations into drawing up those concepts maps and trying to relate those concepts and the theory to the computations and learning from that perspective. That can be life-changing in terms of your approach to mathematics. And I've definitely seen many examples of such cases. There was another student at UCT who had very low marks, and we had 5-hour discussion once. And the next time the test comes, he got full marks for it, and he didn't know his marks, and he told me, he sent me an email, I apologize in advance, I actually didn't have time to prepare for the test. So I probably got a very low mark. That was the second test, actually. The first one, he got full marks for this, the final exam. That's where he apologized. And then I wrote to him, well, yes, you did quite poorly. You got 90 out of 100. And so mathematics seems difficult. It seems technical. It seems a lot going on and complex and everything. But once you break through a certain barrier, and that barrier is turning the concepts into who you are in some sense, making it part of yourself, then suddenly mathematics becomes very easy. And so it's worth trying to break that barrier. It's definitely possible. But of course, it's important to replace frustration with love and passion if you want to break through that barrier. Okay, we are approaching the end for the live stream. However, I started a bit late, so I'm going to finish a bit late. Okay, now finally we got the link to the picture that we were referring to above, something not being zero, not being a solution. The exact quote is, "The set of solutions of a non-homogeneous linear differential equation is not a vector space." And you see there, we are talking there about non-homogeneous linear differential equation. So that's a non-homogeneous linear differential equation is a linear differential equation where you've got this differential operator applied to function y on the left-hand side, and on the right-hand side you don't have the zero. Instead of that, you've got some other thing, some other function g, which is not zero. So that's when we say that the equation is non-homogeneous. And when the equation is non-homogeneous, then solutions of the equation will not form a subspace, and specifically, one thing that will break is that 0 will not be a solution, because d of 0 is 0, and 0 isn't equal to g, since we said g will not be 0 in the non-homogeneous case. So so I hope that clarifies. So there is actually no mistake in the textbook. This paragraph is unrelated to the previous paragraph. In the previous paragraph, the example equation was a homogeneous equation, but now in this paragraph we are talking about a non-homogeneous equation when g is no longer 0. Okay. Yes, another thing, by the way, that's a useful hint in terms of reading mathematical text is attention one wants to pay to specific words that make up the sentences, especially those words that either describe concepts or describe the logical structure of the sentence. Let me give you an example of this. Suppose I tell you, if x is bigger than 5, then x is bigger or equal to 5. Do you think this is true or this is false? Now, surprisingly, many students, when I ask the question like this, they say, how can x be bigger or equal to 5 when it's definitely bigger than 5? But that's the whole point of being bigger or equal to. This means this happens or that. That thing is true when at least one of this or that is true. So just like x being bigger than 5 forces x to be bigger or equal to 5, also x being equal to 5 forces x being bigger or equal to 5. In fact, I think it's this example that sometimes confuses students. So you see, whether something like this is true or not relies a lot on how we understand the concept of bigger or equal to. Also, it relies a lot on the logical structure of the sentence. If then, what does that mean? With mathematics, there is a big difference between having if then in one direction only and having both. And when we have both, we usually say, put an arrow with double-sided. So if I had to reverse the direction here, I would be then saying if x is bigger or equal to 5, then x must be equal to 5. And that would be wrong, right? That's no longer true. X being bigger or equal to 5 doesn't force x to be 5, because x could also be 7, right? But the other way is true. If x is 5, then it's bigger or equal to 5. So this is an example of how the logical structure of the sentence is important to read out the correct logical structure of the sentence, because that determines the meaning of what the sentence wants to say. And then the meaning, of course, determines correctness or falsity of the sentence. right? So when you read mathematical text, you do want to slow down and read it carefully so that you think about each individual sentence and unpack what it actually says from the words used in the sentence and also the logical structure of the sentence. So that's why I often say that if you want to do mathematics well, you need to learn to think slowly, because there is a lot of temptation to rush through a text when you're reading something. Okay, so rather read slowly and correctly than rush through it and make a few gaps and mistakes, because those are gonna add up and lead you to nowhere where you want it to be. Arno is asking another question. When applying a rotation or scaling type of transform matrix, is there a way we can know if the order of operations is important without manually testing, like flipping then rotating is different to rotating then flipping? Indeed. Okay, so first of all, let me make a little correction, Arno. When we say that we are applying rotation or scaling, I don't think we want to say on a matrix. I think it's better to say with a matrix, because matrix itself represents the operation of rotation and scaling, unless you meant a column vector, in which case the way you put it there would be right instead of the matrix. And indeed, the order in which we apply the operations matters, and that's a feature of multiplication of matrices which is very different to how we usually multiply numbers. So imagine I have a column vector xy, and I am rotating it by 90 degrees by some matrix, and so let's call this matrix R, okay? And let us also have a flipping matrix called F. Now, rotating this column vector by R, it doesn't mean physically rotating the display, it doesn't mean transposing, okay? It means taking a vector on the xy plane and then rotating that by 90 degrees around the origin, and so the result will be this vector. So this will be R times xy. And flipping depends on which flipping we're referring to. If it's flipping along the y-axis, then would flip it here, so we'll get this vector, okay? So the fact that this isn't equal to this necessarily, it comes from the fact that, you see, these parts here are the same. So it comes from the fact that this is different from that. And that goes back to the fact that we did mention earlier, that if you have two matrices, A and B, A times B is not always the same as B times A. In fact, it's rarely the same. So when mathematical objects refer to some actions in real life, like transforming under a matrix, we lose this commutativity law. With numbers, this law that x times y is equal to y times x is called commutativity law. We lose that when objects are not numbers, but there are certain actions like transformations, like the matrices are. And a very good example of that is the following. Imagine A is the action of me putting a t-shirt on, and B is the action of me putting a coat on, right? If I first put on a t-shirt and then I put a coat, the result of that will be quite different from first me putting a coat and then putting a t-shirt, right? The other one being a funny outcome. So when mathematical objects represent actions like matrices do, we don't have this commutativity law, just because in real life actions do not commute. If I first break a vase and then try to move it from one table to the other, that the result of that will be very different from first moving the vase and then breaking it, because I might not be able to collect all the pieces of the vase, of the broken vase, successfully, right? Anyhow, when I break them, they will be arranged in a different order as well, if it's on the other table. Okay, maybe that example wasn't a very successful one, but at least the code example should help. Now, coming back to the question whether there are certain situations when we can be sure that AB is the same as BA, The answer to that is, well, it's almost never the case, so we don't really have a general description of those situations. Then you've added after that, so the reason why we can rotate then scale, or scale then rotate, is the same because scaling is multiplying by a scalar. That is right. That is very true, Arnaud. So when one of these matrices represents scalar multiplications, when the effect is the same as scaling, then it becomes a number, and so a number times a matrix, then the order doesn't matter. So then this is equal to that. So scaling is an example of a transformation which does commute with all the others. So if A was scaling, then it's fine. This equality holds. There is a whole theory in algebra which studies such objects that commute with others, like the scaling does. These objects are called to lie in the center of the algebraic structure you're considering when they commute with everything. So it's an important mathematical concept of commutation with other things, and in general, two matrices do not commute with each other. Okay, so that brings us to the end of this live session. I did make a suggestion that if you had if you had any special requests for videos, that you could forward them to me, but nobody forwarded me any request, so I didn't make any additional videos for now. But if you do have any special requests, please let me know. I'll be very happy to make videos for that, and then we will put the videos in the Sunlearn live mathematics folder. And if you would like to have a live mathematics session before the A2 paper, I'm also very happy to do that. You would just have to arrange for the time for that with other students, and perhaps put it up on the Engineering Mathematics 1 WhatsApp group. Okay, thank you everyone for your participation and for joining, even if you didn't participate in the discussions. And I wish you all the very best for your upcoming exams and tests, and just let me know if I can be of any help in mathematics. Goodbye.